think we're right on time for the next talk.
Yeah, let's keep also this second of screen break. So our last speaker of the day actually is Rafael de la Guardia Gonzalez from Intel Corporation, which I believe needs no introduction as a company. So since I see Rafael, all right, yeah, I can see already his screen. So Rafael, as soon as you're ready, you can take it away.
I think you're
I think you're
muted,
muted.
Rafael.
Yeah.
I'm sorry. It should be okay now, right?
Yes. Yes.
Okay. So thank you for the invitation. It's been a great workshop, and in my talk, I'm going to talk about one aspect, a couple of aspects that are, I think, important for having practical robot swarms in the real world. The first one is the capability for even a single agent or a single robot to operate autonomously, robustly by itself, even when it's not yet part of a swarm, and to do that with limitations in computation. So it has to be able to navigate autonomously using only onboard processing and sensing, and with as low computation as possible. And then the second part is that it should be able to then collaborate with other robots to coordinate their movement and share important information about the environment and about the intentions to be able to execute some task. So in particular, I'm going to talk about autonomous navigation of quadcopters in cluttered environments. And this is work that was done in my team, and in particular, with I want to mention the names of my teammates: David, Jose, Leonardo, Rodrigo, and Anthony. And so with that, let me just go to the material. So this is work that we have been doing in my group, which is called the Multi-Agent Autonomous Systems group. We are part of Intel Labs. We are based in Guadalajara. And for the last few years, we have been exploring how multi-agent autonomous systems can move and coordinate their movement and activities, and creating algorithms and capabilities for robust autonomous navigation and decentralized online planning in small and lightweight micro air vehicles. So for robust autonomy requires to have perception, planning, and mobility, very good capabilities in all of these three areas. They also require some important aspects like multimodal sensing, scene understanding, and communication and control. And so we focus on the perception, planning, and mobility, but we cooperate or collaborate with other groups in Intel Labs that work in the other aspects as well. So the insets show the kinds of micro vehicles that we use. The bottom one is used to be an Intel product called the Intel Aero Ready to Fly Drone Kit. Its micro vehicles are generally considered air vehicles under 2 kilograms. So the Aero weighs around 1.3 kilograms. We also developed a swarming quadcopter in my lab that weighs about 200 grams with cameras. Unfortunately, that project was stopped, and we only have about 10 of those that we were able to complete and make them operational. So okay, the problem that we're going to that I'm going to describe in this talk, in the first part of the talk, is the navigation for a single agent, in particular when it wants to reach a goal in an unknown cluttered environment. Then in the second part of the talk, I'm going to address the extension of this problem to the multi-agent case. So for the single agent, the requirement that that the robot is able to navigate autonomously using only onboard capabilities means that it needs to use onboard sensing. So it cannot rely on external positioning. So it has a limited field of view, and it has to use the information acquired from its sensors to reach the goal. So the goal is given as relative range and veering information from the initial position of the robot. And in the environment, there can be many kinds of obstacles, including possibly large convex shapes that will create situations where the robot needs to get out of these obstacles and by retracing some of its path and choose a different direction from the directions it has tried before to reach the goal. So that means that it needs to create and maintain a map of the environment that it uses to navigate. All right. So this is an algorithm that we created that solves this problem. We call it the out-of-the-pocket algorithm. And the three main components of this algorithm that I will describe in more detail are the map creation, the stochastic planning, and then the generation of feasible trajectories that respect the dynamical constraints of the robot. So in terms of mapping, there are two requirements that are important that we wanted to achieve. One is the map representation needs to be capable of fast updates when new information from the sensor is available. And the second is that since we need to replan very frequently to manage the limited field of view and the cluttering environment, then we need to be able to do very fast collision checking. So the solution that we found is that to use an octree like typically done in robotics like Octomap, but we use a type of octree called a linear octree that maintains the same structure of the regular octree, but only stores the leaf nodes. So that allows it to that trades off some memory with speed, and it uses a spatial code that takes into account the XYZ coordinates of every point to uniquely map it into a cell in the map, taking the level of the map into account. So that provides a structure, right? So we have the XYZ coordinate and the level. We put that information to create a special code, and in that way we can map any point in the octree any point in a point cloud, for example, into the map. So empirically, this is a very useful approach when you for collision checking when you have sparse maps or sparse environments, because the number of voxels that you need to check is very reduced, and you can see some empirical evidence here, where compared to using a flat grid map, where as you increase the distance between points in a random map, then the time it takes to check collisions increases with the length of the distance between the points, and whereas in the linear octree that time remains more or less flat. So the second aspect to mapping is updating the map when we have new information from the sensor. So in this case, we are considering that our sensor is typically a depth camera, where we can translate the pixels in the image, in the frame, into points in a point cloud. So the requirement or the goal that we wanted to achieve was to only update each voxel at most once every time a new frame becomes available. So to do that, we use the properties of the linear octree. So we take the points in the point cloud, generate apply the hash function to map them to voxel at the lowest level of the map without actually storing them yet into the map. And then we count how many points are detected into each voxel, and use use that information to update the state probability of that cell using a model of the camera of the expected number of points that we would expect for a point detected at a certain voxel relative to that has a relative position to the origin of the camera. So for other voxels inside the field of view that are in front of obstacles, but were not detected, we apply the stereo error model from this paper by Schauwecker and Zell to update their state. And for the remaining voxels that are not detected, are not inside the field of view, then we do nothing. So that's how we do mapping. Then the next part is stochastic path planning, and for that we use more or less a standard stochastic planner called the RRT Connect. This algorithm expands simultaneously two trees, one from the current position of the robot and the other from the goal. And what we the thing that we do differently here is that we want to sample the points, or to expand these trees in a way that guarantee that the initial portion of the tree is going to be contained in the field of view of the robot, where we know that the space is going to be free for the robot to move. So in order to achieve that, we take advantage of the information that we got from the last map update. So we know already what voxels are free. And first of all, if there are no free voxels in front of the robot, then we know that we cannot move forward. And then the solution in that case would be for the robot to just rotate in place. Since it's a micro air vehicle, it will hover and turn around the y-axis to find another orientation that will actually has some free space in front of the robot. If there is free space in front of the robot, then we already have from the map update the location of the free voxels with respect to the robot, and we can just extend rays towards the central node and add them directly into the tree. And then from then on, we can just expand the tree from the endpoints of these rays, and that will guarantee that at least the initial portion of the tree of the solution will be inside of the current field of view of the robot. So that will ensure that at least that whenever we move forward, we will guarantee that the movement would be without collisions, because it will be in points that are known to be in the free space of the robot. So the next part is the trajectory generation. So for trajectory generation, we break the problem in two parts. The first part is to design a virtual control that induces an equilibrium point for the robot from its current position and some invariant sets around it. So in this figure, eta is the equilibrium point, and then E is an invariant set that is it's generally a space in the dimensionality of the state space, which for the quadcopter drone is a 14-dimensional space. But for this view, we only plot it in 2D. And it ensures that it has the dimensions guarantee that it is safe. Wherever the robot is inside this set, it is guaranteed to be collision-free. So the second part of the solution is a strategy to move this equilibrium point along the path that we created that we found with the stochastic planner. So in this second frame, we have the red line with the dots are the points from that are generated by the stochastic planner, and the green dot is the current position of the initial position of the robot. So we want to then move the equilibrium point along this red line in a way that it guarantees two things. One, that movement is always advancing, moving forward to the final waypoint. And to do that, we parameterize the equilibrium point eta with a phase variable s that moves always with a positive velocity. So that guarantees that the equilibrium point is always moving forward towards the final waypoint, or towards the next waypoint. And then second, we ensure that when the equilibrium point doesn't move too fast. So in particular, initially the robot will be coincident with the equilibrium point, and then as we move this equilibrium point along the red lines, the robot will try to follow. So this is the real actual physical robot. The green line shows how it moved, and you can see that when the position of the robot is close to the boundary of the set, we need to make sure that the equilibrium movement slows down. So by setting the velocity s close to 0, and that will allow the robot to catch up with the movement of the equilibrium point and guarantee that it stays inside the safe region. And because the velocity of the equilibrium point is always positive, it will eventually reach the final waypoint. So that's the trajectory generation, and that respects the dynamical constraints of the robot, and that is guaranteed to be safe. And then these are some benchmark that show that we can actually implement this in a real robot, in a real system, and that it has some advantages. First, in terms of computation time, the optimizations that we did on the mapping allows us to achieve very fast processing for map creation compared to other approaches. And then in terms of once we have the map information updated, the time it takes for us or for the system to generate a new velocity command or a new command for the robot to move is also about two orders of magnitude slower than or faster than alternative solutions. And this is because we avoid using online optimization, and the method is And so we're able to show to obtain a solution that respects the physical constraints of the robot without doing optimization online. So in terms of performance, you can see some simulations in a random forest environment, and you can see that in terms of the success rate, our method is able to get very high success rate even in a very densely cluttered environments compared to other algorithms, and and also allows the robot to move with relatively high velocities, or it can take more advantage of the full dynamic capabilities of the system, so it can navigate also faster than the other methods. So here are some simulation results that show in particular the out-of-the-pocket capability, right? Where we have the robot is able to reach a goal where it needs to explore and change direction and navigate in some tight spaces. We did try to solve this same environment with the other algorithms, but we're not able to do that with them. And one of the main reasons we think that we are successful is because of that the methodology ensures that the movement is also within the field of view of the robot, and we make sure to align this field of view with the direction of movement, taking the dynamical constraints into account. So the combination of these things allows the robot to guarantee that it is always moving in a direction that is safe and is collision free, even when the goal, for example, in this case, is on top of directly on top of the quadcopter. So the quadcopter, if it just goes up directly, it would collide with this obstacle in the middle that it is not able to see because it's outside of the field of view. So it needs to slowly climb by going around the obstacle. And we do have some experiments. We implemented this in a low-cost, small and lightweight micro-air vehicle, and we're able to demonstrate this in simulations. You can actually look at follow the links in the presentation and look at the multiple videos online that show the performance in the real world. And for the interest of time, I will not show the videos right now, but want to move to the next part, which is the extension of this work into the multi-agent case. So let me just quickly check time. I have a couple of minutes, so I will just very quickly describe the main ideas that we apply to solve this problem in the multi-agent case. The problem is very similar, except that now the robots also have the ability to communicate within a certain distance of each other. And the solution is also similar, but we need to have 3 additional components, which is one, we identify sub-goals in the environment that we use to make progress and avoid conflicts between the agents. And then the second part is the communication, where we share local goals and local map updates with neighbors. And finally, we apply a cooperative stochastic planning algorithm to solve the problem. And so very quickly, just the solution uses an algorithm called the discrete RRT that was proposed by Shom, Solovey, and Dobson. And basically, it achieves scalability by limiting the search in the composite configuration space of the product roadmap for the agents. And it uses an implicit representation where we check extend the map. When we extend the tree, we check collisions and only add nodes that we know that we are collision free, and take advantage of a very useful heuristic that we have in terms of the cost to go that we have from how we construct the problem. So to be able to solve the problem using this DRRT, we first need to take our solutions from the stochastic planner for the single agent case and convert them into roadmaps that are needed for the distributed RRT. And we do that using the K-best solutions from an RRT planner. And we have some initial results that show that it is possible to use local frontiers that are extracted, that are identified by the agents as intermediate goals that guide the robots to not only guide the robots to move towards the goal, but also allow them to avoid conflicts. So by having multiple frontiers and having the ability to exchange frontiers as goals for the multiple agents, then we can have them avoid conflicting trajectories, and in this way the robots are able to very quickly find solutions cooperatively, so much faster than if there was only one agent in the environment, right? So this also applies to exploration, where we can have multiple frontiers, for example, in the map identified, and then we want to quickly explore all of the frontiers using a team of agents. Then using the same algorithm, then each the agents coordinate to explore all the frontiers, and then finally approach the goal when all the frontiers have been explored. So, and I will stop here, and I don't know if there's time for questions.
All right. Yeah, thank you very much, Rafael. That was an extremely interesting talk. I think we have like very, very little time for questions. Maybe if you could tell us, like, or illustrate us the domains of application that Intel is looking at, in particular for the multi-robot case.
Sure. So we are we are in talking with different customers that work on exploration. For example, some of the applications that were mentioned before, like exploration in disaster cases like fires or earthquakes, and also looking at industrial applications for coordination in warehouses, for example.
Yeah, sounds good. And actually, may I ask you to go to the Q&A page on the workshop website? So if you have time, there is, I think, one question for you, so you can answer it directly on the website.
Sure.
All right. Yeah. Thank you so much. Thank you once again, Rafael. And I think let's move on to